Hello there, I'm playing with junk again. This time I have a clock. This is a slave clock and this is the master clock. The master clock is a Swiss-made Favag Cristaltime M. It has a 10 kilohertz quartz crystal inside and some electronics that divide this 10 kilohertz to a 1 minute impulse, and the rest of the clock is a mechanical clockwork that shows the time, and then the minute impulse goes out to the slave clock, which can be this model here, or a simple slave clock with clock hands, a mechanical one. Well, this is a mechanical too. It's a Solari clock from Italy, from the beautiful town of Udine. The model is called Dator 6. Because it shows the date too. It's not only clock. And I try to show you how it works and how you set the date, the day, the time, and all that stuff you need to set up a clock. The problem with this slave clock is it looks great, but it is a little bit difficult to set up, because when the back cover is on, you only have two buttons. One button advances the minutes and the other button advances the hours. And for example, if you want to set the date, you have to push the hour button about 1,000,000 times, and that's a little bit difficult. So if you want to set the date, you have to unscrew the back cover and do some mechanical magic, but you first have to find out how it works, because this clock does not only change the month correctly, 30 days, 31 days, February 28 days. It also knows when it is a leap year, so you have to set the correct year. There is a wheel with 4 times all the month. One set of the months is colored red, and that's the leap year setting. And 2016, this year, is a leap year, so we have to set that. Let's see inside. It's a little bit too big to use the tripod, so I have to hold the camera in my hand. Here is the motor, if you want. As you can see, it says 24 volts, 1800 ohms. Diameter of the copper is 0.14 and SP is 23,500. I don't know exactly what that means. Maybe the number of turns, the number of windings, not sure. It works very simple. Every minute it gets one pulse, a positive pulse, and the next minute it gets a negative pulse. So it advances one of the gears. You can't see very well here. Oh, here is the magnet. That's the electromagnet, and that's a permanent magnet. And this spins a half a revolution every minute. And at the moment I'm spinning the wrong way. Okay. So every minute it gets a positive pulse, advances a minute, then it gets a negative pulse, does the other half circle of the magnet, advances a minute, and that's everything that movement here is doing. I have disengaged this spring here because when I have to turn many hours, it goes too hard when there's a locking mechanism that locks the hours in place. So that's the wheel to turn the hours. And when 24 hours are gone, the day and the day number are advanced in the same time. And this here is the mechanism that makes the number of the day corresponding to the correct month. And as you can see, there is a wheel with numbers. The numbers are the numbers of the month, and these numbers here have a white background, so that means it's for a regular year. And if I advance, this wheel here advances the number of the day, and how does it work? Oh yes, I need something to point. There is a gray and red wheel that are connected together. Every time the number reaches the last number of the month, this gray gear is engaged by the white gear here, and moves the red gear, which moves the black gear here. That changes the month. So I can change the month manually here, and you see there is a spring here, there's a clutch, some kind of mechanical clutch here. I need a longer screwdriver. Sorry. And I need more light. Okay. And I need a smaller camera. So this is the clutch. And if I turn the month by hand, the red wheel jumps over the gray wheel. Now I have disadjusted the month, so I don't know at the moment which month the mechanic has set and which month I am showing at the front. So what we need is to advance I have advanced the clock a little bit, so now you can see the trick. There is a little red tab here, and that shows now, I hope you can see that, it is more or less on 7, so this tab corresponds to 7. That means the 7th month should now be on display in the front. That's July. Let me see what we actually have. June, July, okay, that's okay. So I just advanced the month wheel here until it corresponds to the setting of the gears. Now, as you can see, it seems that the month gear here and the day gear, they are almost spinning the same speed, but every revolution of the day gear, the month gear advances 1 month, and this is because this gear has a couple of teeth more than this gear. It's a little bit smaller, and as you can see, they are connected with this double gear, with this axle here, and since the big gear has a couple of teeth more, I don't know, 1 or 2 maybe, this gear here spins a little bit slower, and it is exactly that slow that if this gear makes 1 revolution, this gear makes 1 revolution minus 1 month division here. It's a little bit complicated to explain, but let me try. We are now on the 7th month. Hope I hold the camera correctly. This is a little diagram I made. The red part in the center is a movable shutter that in the 31-day position it blocks the opening inside the wheel, so the long red tic-tac bar has to step through all the 31 days. And when it is, for example, in the 28-day position, the red wedge, then it opens the inner circle, and when you follow the yellow line or the orange line, you see it jumps 3 days until it locks to the first day of the month, and that's how the number of days are adjusted according to the month. I can also advance the mechanism by pulling this lever here, and now you can see that the red tab here points now to the middle between 7 and 9, so it's the 8th month. After 1 revolution we have advanced 1 month. It's a little bit, I don't know exactly where to read, maybe we should read it down below, it's a little bit more precise, but I think you get the idea. Now, the problem here is, for example, if we have a February with only 28 days, we have to jump 3 days to the March the 1st, and this is done down here. This is the lever that advances the day date 1 number, and there is a mechanism which is attached to the month wheel that opens or closes some gaps here, and when the lever goes back it falls into these gaps and jumps a couple of days according to the month. The problem is this has its own spring, so the drive, it is driven by this metal gear here, and you see that the plastic gear is not moving at the moment because the spring is too weak now, because I advanced it here by hand. So I have to wind up the spring first, and now it starts jumping. And this spring is necessary because, for example, February you have to jump 3 days, and you need a little bit of power reserve to jump the days. You cannot just have a direct gear transmission. You need something, you need some kind of mechanical buffer to jump the days. So that's what happens here. Okay, now let's say you have the month. You advance until the month changes, then you have to set the number correctly. So if you have exactly the moment when the month changes, then you have to set the number to 1, of course, because the first day in the month is the first day in the month. And to do this, you can open these screws here, and then you can rotate the day number 3 until it shows you the correct number. You can also open these screws between the hour and minute part. Hours here, minutes here. You can see it from the wear. The minutes are worn a little bit more because they rotate, of course, a little bit faster. You can divide the mechanic by losing the 2 screws here, and then you can turn that part, the part behind here, free. So to set the day, you simply turn that wheel here. There is also a mechanical clutch similar to the other one, which does simply this. And you see the notch here on the white wheel. That's that engages the gray wheel here, the gray gear, to advance the day. So every 24 hours this white wheel does 1 revolution and takes the day name. Let me show you that. Now you see it takes it 1 step forward. Again, 24 hours, 1 day forward. And if everything is adjusted correctly, the day will change at the change between 2300 and 0. It's the 24-hour format here. Okay, 18, 20, 1, 2, 3, Wednesday. And the number of the day changes in the same moment. Let me see, September has 30 days. Let's see what happens. It jumps to 1, from 30 to 1, that's okay. But the problem is the September stays until I advance to about 5 hours. Then it switches to October, so the month here is a little bit late, but there is no way to change that. Okay, let's have a look on the electronic part of the mother clock. This is the Cristaltime M master clock or mother clock from Favag SA in Neuchâtel, Switzerland. And what's inside looks like this. The slave clock, the Solari from Solari Udine, is about from 1980, and this one is a little bit older. So the date code on the chips tells me it's from 1972. And let's have a look what's inside. It's not an atomic clock, it's just a crystal clock. But it has a little special feature. First of all, you have seen on the slave clock, it works with 24 volts, so the magnet is made for 24 volts. But this one is puts out only 12 volts, but it turned out that everything works perfectly, even with the lower voltage. So, do not take away this protection. Yes, that's exactly what we want to do, because it's very easy. There's not much to see, but inside this metal block here is the crystal. So I'm not entirely sure. I think these are the connectors of the crystal. There is a thermistor that measures the temperature, because the whole thing here is a crystal oven. So this crystal is heated up to about 50 degrees centigrade and kept at exactly that temperature. Oh no, okay, now I see. This is the crystal here, embedded in this chunk of aluminium. And the other contact here that goes through the block is in fact a resistor that heats up the entire metal block here to a temperature that is detected by this sensor here. It is compared by this 741 op-amp. It is possibly adjusted by this potentiometer, which I will not touch. And I said it is 10 kilohertz, which is wrong. It is 100 kilohertz. I made that label myself because I adjusted this with my atomic clock reference. So I could explain that, how I did it. So to adjust, you can go through the front panel to that adjustment. It's a variable capacitor, a ceramic capacitor. You screw that screw in or out and it changes the capacity. There's another capacitor, it's the, I think it's the coarse setting, but it turned out that it's reacting a little bit weird when I turned that, so I left that as close as possible, and then I turned this one. So the 100 kilohertz come out at pin 2. So there are 3 pins here, ground. One is voltage power supply, and the middle pin, number 2, is the output that goes to the board below. And the board below, as you can see, SN7490, that's a binary counter. That's a whole row, 1, 2, 3, 4, 5, 6. So what they do here is totally simple. They divide 100 kilohertz by 100,000 to get 1 hertz impulse. And then they have a further divider. I think, well, it's certainly part of this. They further divide that by 60, so you get a 1 minute pulse. That 1 minute pulse goes to I think the 7400 is used as a flip-flop. It's two NAND gates, if I remember right, or two AND NAND. With two NAND gates you can make a flip-flop, and that flip-flop drives through any transistors. Yes, we have two transistors here. Drives these read relays here. That's the coil here, and that's the relay, the read relay contacts here. One relay for the positive pulse and one relay for the negative pulse, so they change polarity. So 1 minute this relay gets energized, and the next minute this for 1 or 2 seconds. That's enough time to advance all the clocks in a building, all the clock hands, by 1 minute. It also drives the mechanical clock here, which has a similar drive like the Solari slave clock. Let's put that on again. There is, oops, let's turn that around. There is an electromagnet. It's just one coil that gets the pulses from the relays here. There is a magnet, a rotating magnet here, that does 1/2 rotation every minute. So, and that's the reason why you need a positive and a negative pulse, because the polarity of that magnet changes, and then you have to change the polarity of the electromagnet too. And you see it advances the big gear here 1 tooth every minute. It's not a second. It doesn't have a second hand, it only has a minute hand. That's doing this. 1 step, 1 minute. There are 2 switches. One says stop. This is for setting the time. This one is to advance, to make manual pulses to advance the clock. If you have the exact time, you can stop the clock until you have 0 seconds, and then you release that and you are exactly on the second. Let me show you that. Let's plug it in. Okay. Oh, you have to set to remote or whatever. Now you can set the time, positive pulse, negative pulse, positive pulse, up and down. And if you, okay, yeah, it just jumps 1 minute further, but you can hold it on stop until the seconds, until the time is exactly set, and then you release that and it works. Now let's see from this position. First remote. And now you can see you cannot change the time too rapidly, because that's about the maximum, because you have to make sure that all the clocks in the building are doing exactly the same. You cannot afford that one clock misses a minute or two. Now we have, I better unplug it for safety reasons. We have a transformer here, nothing special. We get in here from the cable, the old wiring code, black, red for I think neutral and hot, but it could also be the other way around. I had to check that. We have a fuse, we go to the transistor, we have a filter here. Then we go down to the board with 2 windings. There's the rectifier with only 3 diodes, so I think they use 2 diodes for the rectifier and 1 diode has another function. Then we have a couple of capacitors which I changed lately. The original capacitors are of course about 40 years old, so I thought it could be fine to replace that. Then we have an LM109K, which is a 12 volt regulator. There is also 2 wires that were connected to a battery, which was placed here. They use 2 6 volt batteries in series, so we have a 12 volt supply for the entire box here, which will also supply power to the clocks. There is another transistor here to regulate. Yes, I think that's in some sort of slave regulator of that one. Here you can adjust the voltage, and there you also have an output where the 100 kilohertz come out, so you can connect some measurement, some adjusting meter here, and then you can adjust the clock exactly to the fraction of the second. On the back side is some screw terminal. Some nice guy wrote here that terminals 7 and 8 are for the clocks, so terminal 7 and 8, the blue wire here, that's where the other clock is connected. If you are interested in some details, some numbers, I'm pretty sure you won't find a lot about this because the company does not exist anymore, or at least they don't have any documentations about this. But well, that's it. Thanks for watching.